For this part of the assignment, I decided to redesign the original lesson plan into 2 lessons, which are approximately 65 minutes each. The original plan had some useful features, including explicit modelling, using mini whiteboards, progression, and an exit ticket. But it was trying to move students from recall of multiplication facts to independent use and then explanation of area models, all within one lesson. Now that's a large jump, particularly for students who are still novice learners in those earlier multiplication skills and prior knowledge areas. I felt that learning this new concept would work better over multiple lessons. And so I looked at the New South Wales and Victorian curriculums to see what they're doing. Both of those states used multiple lessons and were placing area models in the middle of a multiplication sequence. They were front-loading with multiplication facts, patterns, arrays, then moving into area models. After this, they would move on to worded problems, which I've incorporated, and then missing numbers, which I haven't incorporated. But this would make a logical next step if I were to create a further lesson to follow. Okay, so let's dive in. The original introduction only retrieved 4 multiplication facts. It stated that students had prior experience with repeated addition, arrays, partitioning, and place value, but it didn't really check whether those schemas were available or accurate within the students. The lesson then moved quickly into 23 times 4, which was modelled by the teacher, followed by 1 guided example. Now, this is not sufficient to understand a new procedure or to build a new schema for this content. The lesson then had a very busy, long and visually overwhelming worksheet that every student completed. There was no differentiation. If there was, it was used as extra time, a fast completion, or using peer help with additional questions. This doesn't meaningfully adjust the process product in response to readiness, as we know Tomlinson advocates for. It also risks labelling speed as mathematical expertise, but we know that expertise is better understood as having well-organised, retrievable schemas that support efficient problem solving. The worksheet created another concern. It included many questions, and one of which was a 3-digit multiplication question, but the curriculum doesn't introduce this until year 5. It had lengthy instructions at the top, some novelty pictures and other choices which really overloaded the student. Much of this information increases the extraneous cognitive load for the students and doesn't actually connect to what they're learning. The exit ticket also asks students to solve 1 calculation and then to write an explanation over 2 sentences. By doing this, it checks the students' literacy skills and their ability to express reasoning. And I feel this could have been simplified so that it's not the focus. The focus and the check should have been on whether they have actually learned the multiplication procedure that they're being taught. My redesigned lessons separate the initial acquisition from later application and extension, while keeping assessment closely aligned with what was being taught. Lesson 1 begins with a 20-minute activation circuit. Within this, students will retrieve partitioning, vertical addition, multiplication, repeated addition, multiplying by tens, and then interpreting word problems through arrays. This is much broader than those original 4 questions that were asked in the original introduction. This connects with all the schemas, not just multiplication facts alone. This is a low pressure activity with some movement, mixed ability groups that facilitate those great peer conversations. This opening serves 2 purposes. First, it brings relevant information from long-term memory into the working memory before students are introduced to a new concept and model. Schema activation can reduce working memory demand because students are not processing every element as completely new information. Second, it gives me, the teacher, a diagnostic piece of evidence. I'm listening to discussions, I'm checking recording sheets, I'm seeing them using their mini whiteboards, and I'm getting that private confidence rating that all let me identify which students have secure schemas and which students might have some gaps or misconceptions. This matters because novice and more expert learner status is specific to the station or the task. While the student might know their multiplication facts, they might still be novices in partitioning or interpreting arrays. There is optional extension here for within each station, but it's discrete. Lesson 2 also begins with another true or false quiz, so that the students are retrieving those same connected ideas again after a time gap. This creates spaced retrieval and supports transfer back into long-term memory, rather than relying on a single exposure. After the activation circuit, I use clear, gradual release sequences. I do, we do, you do. This was present to some extent in the original lesson, but I have made it much more explicit, and I've added more guided checking before the independent work commences. Rosenshine 2012 recommends presenting new material should be done in small steps, modelling it, asking frequent questions, and checking the responses of all students before moving on. In the I do phase, I model 23x4 with base 10 blocks, a drawn area model, and mathematical symbols, and a think aloud. I deliberately connect these steps back to every step of the circuit stations. The spoken explanation and repeated vocabulary, including factor, partition, partial product, engage the phonological loop. The blocks, the colour coding, the area diagram engage the visuospatial sketchpad. The central executive must coordinate attention across these sources. So I keep colours and the 5-step process consistent, and I remove those decorative or unnecessary parts of the information. Badley's model reminds us that these systems have limited capacity, so the visual and the verbal information must complement each other rather than be competing. The model links the concrete materials, the pictures, and the symbols. This broadly aligns with the CPA, Concrete Pictorial Abstract approach, and also the ELPSA model, Experience, Language, Pictorial, Symbolic, and Application component. From a cognitive load perspective, the intrinsic load comes from the interacting elements students must coordinate: place value, partitioning, multiplication, and addition. While I cannot remove that complexity without changing the mathematics, I can help and sequence it. So I use work examples, visual prompt card, and doing one step at a time to help reduce extraneous load. The productive or germane load is then directed towards noticing why the model works and integrating the representation with existing multiplication schemas. The guided phase is designed around Vygotsky's zone of proximal development. Here, students solve 42x5 and a worded problem with support that is responsive rather than automatic. Through the use of mini whiteboards, I can see every student's thinking and steps, not only hearing from those confident volunteers who put their hands up. If a student can proceed, then I reduce the prompts. However, if they are close but stuck, I can provide supports like partially completed area models, a prompt card, multiplication charts, or base 10 blocks. These are temporary scaffolds that are intended to help the student to step through anything that they cannot complete independently just yet. Importantly, the teacher does not immediately take over. I first ask prompts such as, what could you petition first? Or which known fact might help you here? Or does that part of your diagram represent something? This gives students time to retrieve that information, reason, and do the self-correction. Productive struggle is not about leaving novices unsupported. It means giving some wait time and the least intrusive prompt needed that preserves the student thinking while keeping the task within their zone of proximal development. The You Do section in Lesson 1 is an independent worksheet, which is clearer and has a larger area for working out than the original. It has 3 number sentences that come with provided algorithm and model scaffolds. It has 3 number sentences without these scaffolds and 2 worded problems. In addition, there are 2 optional extension questions on the second page. The worksheet's design is intentional as it increases difficulty, removes scaffolds incrementally, and positions those higher level questions on page 2. So they're not visible, helping novices not to become cognitively overloaded. The novice learners may only do page 1 or the questions that have pre-drawn frames. They are able to use the prompt card, concrete materials, and seek assistance if needed. Lesson 2 begins by retrieving the 1-digit area model process through 10 true or false questions. Here, every student responds on their mini whiteboard, and we answer the questions one by one. This gives the students immediate feedback, but also gives the teacher formative data and uses error correction to strengthen the students' schemas. I then explicitly revisit 34x6 and guide 27x4 as a whole class, ensuring that students' understanding is secure before introducing our 2 2-digit factors. This progression from 23x4 to 23x14 is deliberate. Students are not learning an entirely new strategy. They are integrating a new idea into an existing schema now. When both factors are partitioned, the model contains 4 partial products rather than 2 like they've just learned. I keep the completed 1-digit model visible beside the new 4-digit model so that students can compare what has stayed the same and what has changed. This supports schema integration and, where a misconception exists, conceptual change. The I do, we do sequence continues. With number sentences and worded context, I explicitly model estimation here, and I use a vertical algorithm because the original wording about combining partial products could leave novices a little bit unsure of how to do that. The think, pair, share then asks students to explain why an area model is useful. Now, unlike the original exit ticket, this reasoning occurs after substantial modelling, and it has a word bank, oral rehearsal, and sentence starter available. The product of this will likely begin as spoken language before it becomes one agreed written sentence between the pairs. So this supports the phonological loop through rehearsal and elaboration, while the diagram remains available to support their visuospatial sketchpad. After our think, share, pair, we move on to Goatbusters. This digital application is intentional to help break up the lesson and make it a little more engaging for our young learners. I specifically chose Goatbusters because it's an Australian-made application. It's developed by Monash University and is freely available from ABC Online. It is used after explicit teacher modelling and guided practice, and it is certainly not a replacement for teaching. All students work towards the same concept within Goatbusters, with an extra level of challenge for those students who are ready. Novice learners may always stay at level 1, but they can also be aided by the base 10 blocks, a multiplication chart, and some prompt cards if needed. I'd expect the more expert learners of my group to be progressing up to level 2, where they're solving increasingly complex problems, 2-digit multiplication, and otherwise they may use the application with less guidance than their peers. As further extension, such as for fast finishers, they can also be prompted to adjust the area model so that the complexity of their partitioning increases. While students work, I will deliberately use questions before giving them straight answers, such as asking, how did you partition that number? Or how do you know if your answer is reasonable? To encourage independent problem solving. And this gives me anecdotal evidence of the students' strategies, not just whether their final answers were correct. A digital report card can then be printed from Goatbusters, which is fantastic. This, along with teacher observations and questioning, provides formative assessment data of students' ability and their understanding. The exit slips across Lesson 1 and 2 are also designed to inform the next instructional decisions. Lesson 1 is checking whether students can independently use multiplication, partition, calculate both partial products, and then combine them using an algorithm. Those results determine who needs further modelling, core practice, or extension in Lesson 2. Whereas the second exit slip has a differentiated and a standard version. The teacher can use either based on the students that they have in front of them and from their observation. The exit ticket uses a worded problem for 23 times 14 and asks students to check Sam's estimation reasonableness. They make an area model, then they identify the steps that they found difficult. The top section here will provide evidence of what the student can do, while the second part is a self-report and provides an additional clue about where the cognitive demand was. It does not replace teacher judgment, but it helps to plan and scaffold the next lesson. These 2 lessons are more appropriate than the original single lesson because they allow time to activate prior knowledge, check prerequisite schemas, manage cognitive load, rehearse and retrieve learning, and then support students to transfer the area model strategy into more complex problems. Thanks.